Welcome, everyone, to Red Planet Live. I am your host, Ashton Zeth. I'm elated to be hosting the Mars Society's podcast and leading the conversation about human exploration of the universe and the future settlement of Mars. As a longtime space enthusiast, I am passionate about STEM education and making humanity an interplanetary species. Thank you, everybody, for joining today and supporting Red Planet Live. So for today's episode, we're going to be highlighting some of the speakers from this year's Mars Society convention in Los Angeles. To kick it off, you will hear from Mars Society founder and president, Dr. Robert Zubrin.
This situation is much more severe than that, okay, because this isn't just one program that is being destroyed, okay? So at the same time that they were abandoning Hubble, they were getting ready to send MRO, the Mars Reconnaissance Orbiter. We had just landed a Sierra Opportunity. We're building beginning to build Curiosity and a bunch of other planetary missions. So in this case, they're going after the whole program itself, not just one important part of it. And this can't be tolerated. Okay, now look, why should this matter? Say, well, okay, you're getting the moon with people on the moon and then humans to Mars. And what are you worried about these little rovers and things for? Okay, well, I'll get a little bit more to that, but first of all, I want to talk about how under the current situation we're not getting the moon or Mars. Okay, Artemis is a total mess. It is a total massive mess because the same irrationality that is allowing this destruction of the space science program is disorganizing an irrational human program. If you look at Artemis, they've got 5 primary flight elements. Okay, the SLS Starship, the Orion, the Lunar Orbit Gateway, and the National Lander, and none of these things fit together. Okay, because none of them were designed as part of an overall system. They were each simply promoted as something pleasing to some constituency that wanted money. So each of this is not a purpose-driven program. This is a vendor-driven program, and it's totally chaotic. Okay, now you could say, well, Starship can do it all, right? Because it doesn't need the rest of these things to do a complete lunar mission. Okay, and that is sort of true, except that if you do the Musk architecture, which is you send a Starship to low Earth orbit, and now you have to believe not just that Starship is going to work, which I do believe, but that it will achieve the performance metrics that are currently being advertised it, which is a whole nother issue. Okay, but if you believe that it really could deliver 100 tons to Earth orbit, and these will weigh no more than 100 tons itself, then you have to launch 4 more tanker Starships to refuel the tanker in low Earth orbit to get it to the Gateway. And then you have to refuel it in Gateway with 3 more tankers, each of which require 4 more tankers to get them to the Gateway. Okay, so you end up with like 14 tankers to do 1 lunar mission. Okay, this is a wildly suboptimal mission architecture. And you also have to believe that you can do these 14 launches within some limited amount of time. And, it's a different universe. Now, so this isn't going to work. And then the National Lander, which uses hydrogen oxygen, is not compatible with the Starship, which uses methane oxygen. Now, if you had leadership at NASA, this technically could be repairable, okay? While no one can convince Musk to also build a smaller Starship, I have tried, I call it the Stardo. That's what is needed, something 1/5 to 1/10 the size of Starship that runs on methane oxygen, and you could then put a Starship in low lunar orbit and have it act as a tanker for a little starboat that goes up and down. That would make sense, and you could use the same approach to Mars, okay? 2 sizes fits all. And so instead of landing the Starship on Mars and having to refuel it with 600 tons of domestically made methane oxygen, you'd only need 50 tons. That's for a direct flight from the surface of Mars back to Earth. You'd only need 50 tons to send the starboat up to the orbiting Starship. And so you could have a 2 sizes fits all architecture, okay, but that would require leadership at NASA. However, the problem is bigger than that, okay, because some people say, well, look, it doesn't matter if NASA is destroyed because Musk can do it all, okay? And this is simply not true. This is not true. First of all, to realize the Musk architecture requires a multi-megawatt nuclear reactor on the surface of Mars. Where is that going to come from? Okay, the space nuclear reactors use highly enriched uranium or plutonium. These are controlled substances. It's going to require government involvement. If you try to do it with solar energy, with the architecture that he's proposed, it requires 13 football fields of solar panels, and so forth. Just officer matters. So you need government cooperation to make this work. But there's a bigger issue, okay? Because you see, look, humans to Mars cannot be done as an Elon Musk hobby horse or a Donald Trump hobby horse. It has to be done as an American program. It has to be done with bipartisan support, or as soon as the fortunes of political war shift, it will be killed. Now, here's the thing. How do you get bipartisan support for this program? You make it not about Musk's desire to have a planet terminus on which a select group of scientists can go and be there to reconstruct human civilization after the Earth is destroyed. This is his tacit, as he calls it, his colony terminus after the one in foundation. Or it can't be done to have Trump win his second Nobel Prize. It has to be done for purposes that are understandable by a broad part of the American electorate and political constellation, and that is science. Okay, if you mark this program with the brand of Cain by having it done by the same people who murdered the space science program, you're guaranteeing that it will be destroyed as soon as the fortunes of political warfare shift. Okay, Musk has defined himself in an extremely partisan fashion, and if this program is defined in this extremely partisan fashion, that will be its fate. On the other hand, if you said, instead of killing the space science program because we're doing this stuff, we're going to use this stuff to radically expand the potency of our space science program. That is, the first Starship landing on Mars, or Starboat, okay, instead of landing a Optimus Tesla mannequin for public relations purposes, it lands a robotic science expedition. Musk says the Starship could land 100 tons on Mars. Let's give them 30. 30 tons is still a lot, because right now we can only land one, so 30 tons. What could they do with 30 tons of scientific payload landed on Mars? Instead of landing one rover, we could land 20. And instead of one little helicopter, we could have 20 medium-sized helicopters, each carry 20 or 30 kilograms of scientific instruments. Okay, and we can have a well-instrumented science lab in the lander to which the rovers and helicopters bring back samples, and they can deploy light detection experiments and drillers and all sorts of things, seismic networks, and everything that you could possibly want to do a science expedition to Mars that would be 2 orders of magnitude more potent than anything we've been able to do with the kind of science program that we've done up till now. So instead of making the human Mars program the murderer of the science program, we make it its enabler. It's greatest strength. Okay, we can do, yes, that needs to be done. But if you're going to do that, instead of shutting down JPL and these other places that make things like Mars rovers and helicopters and such, you need to expand those capacities. All right? Because who's going to make the Mars rovers that would go on this expedition if you're shutting down that whole line of activity? So there is that. So now if you did that, then you turn so in other words, that's how you're exercising the Starship first to get it ready to send humans to Mars. And then you can send subsequent science expeditions, as well as expeditions which are deploying construction rovers and stuff to access the glaciers on Mars and melt water out of them and fill up the Starship on the surface of Mars with propellant made there, using its tanks as your surface storage depot and all the rest. This program evolves naturally from an expanded science program into a human program. And you see, if you do this, then you have the support of the Mars science community for this program. And the Mars science community is university-based, which is to say it's based in a social network that is the left of center, and which has the ear of the Democratic Party. And then you have a program that has national support. And then instead of this program being a must-have course to create the Harry Seldon terminus colony on Mars, it is a national program to once again astonish the world with what free people can do in science. Okay, and this is very important. Okay, because this is the larger issue. The highest ideal of contemporary Western civilization is freedom. And science is the child of freedom. Free inquiry. Okay, is what produces science. Okay, the fruits of science, technology, and anybody can use that. But science itself, okay, comes from freedom. I have to say that this administration, its attack on the space science program is coming in tandem with an attack on American science much more broadly. The National Science Foundation, the National Oceanic Administration, the Center for Disease Control, the National Institute of Health. Okay, and in fact, in some respects, some of the attacks on scientific medicine by this administration are more severe than what they're doing to NASA, because at least they don't actually have a NASA administrator, but whoever is sort of doing that has not yet, issued a denial that the moon exists or something. Okay, which is sort of the case with medicine. But so we're having an attack on science, and once again, okay, if you look at the Enlightenment, okay, the proof given for the desire to set reason free was that it produces science. Science is the poster child for the value of human freedom. Okay, it puts it in terms that are not abstract at all. It produces stuff that saves your child from dying of disease. It produces methods of navigating the sea that can get you from here to there. Okay, and enable global trade. It can do all these things. This is what science can do. Science is magic that works. Okay, and it's a product of freedom. And now, admittedly, say science is not all of science, but it is the greatest symbol of science in our age. It is the banner of science. It is for the scientific worldview what Gothic cathedrals were to the religious worldview of the Middle Ages. Those were represented concrete symbols of the value that those societies put on their highest ideals. Okay, the of human salvation through the grace of Christ. Well, the NASA space science program has sounded the world with the things that it does. It is the images Hubble and the images from Hubble and now from Webb and taking of the outer planets and so forth by these various probes. And yes, from the surface of Mars. These are the Gothic cathedrals of our time. This is the banner of the scientific worldview. This is our flag, and they're burning our flag. That's what they're doing. They're burning our flag when they destroy this program, and it cannot be tolerated. So, to save not just the Humans to Mars program, but to reaffirm the highest ideals and the most productive ideals of our society, we need to repel this attack. Okay? And that is why the Mars Society in the coming period, and we're going to talk more about this, you'll hear about this from James, you'll hear about it at the banquet, okay, is going to be to mobilize, to contact Congress, to mobilize chapters in every district to go to speak to anybody in Congress or the Senate or who can reach them and say, this must not happen. We can't let them burn our flag, and we're not going to let them burn our flag. Thank you.
Now we will hear from Hoppy Price, Chief Engineer of NASA's Robotic Mars Exploration Program.
All right, our next speaker is Hoppy Price. He is currently the Chief Engineer for NASA's Robotic Mars Exploration Program, so he's going to tell us exactly what's going on with that. And he started at JPL, I believe, on April Fool's Day, 1978. Served as the configuration engineer on the Cassini orbiter, and also was the architect of JPL's architecture for humans to Mars. So love to hear what you have to say, Hoppy.
Okay. So this is one of my favorite images here. It's from the Curiosity rover, which has been climbing up Mount Sharp in the center of Gale Crater on Mars. And so in this image, it's in the middle of a channel, which billions of years ago had water running through it. And you can see off into the distance Gale Crater. And Curiosity has been operating for 13 years, thanks to, because we have RTG power supply here, you can see the radiator fins. That's enabled us to operate for 13 years on Mars. It's still doing great science, making fantastic discoveries. We currently have 5 U.S. missions operating at Mars, 3 orbiters and 2 rovers, and then there are 4 non-U.S. missions. So Mars Odyssey, named after 2001, A Space Odyssey, was launched in 2001, and it has a thermal imager, which is really essential for doing some of our landing sites investigations for humans to Mars to do rock abundances. MRO has the high-rise imager, which can image things on Mars down to 30-centimeter resolution. That's also essential for validating landing sites. And in fact, MRO has done some images for SpaceX to look at one of their landing sites at Arcadia on Mars. And then, of course, Curiosity is doing great stuff. We have the MAVEN mission, which is managed by Goddard Space Flight Center. And that's looking at how Mars's atmosphere evolved and why Mars lost its atmosphere. We're understanding how the solar wind blows the atmosphere away. It only has 1/3 the gravity of Earth. So, terraforming Mars in the future is always going to be a challenge because of the solar wind, tending to blow away the atmosphere. So just like John Carter on Mars, they had an oxygen plant there on Barsoom to keep regenerating the oxygen. We might need something like that. And then Mars 2020, the Perseverance rover with the Ingenuity helicopter, has made some amazing discoveries and has a number of samples that we would like to bring back to Earth, which may have compelling evidence as to possibility of there having been past microbial life on Mars. And then the non-U.S. missions, the Mars Express has been there since 2003, still going strong, has a great radar experiment. The Trace Gas Orbiter is a very robust orbiter, and that's really the workforce now for relay operations, getting data back from rovers, but of course Odyssey and MRO and MAVEN are also very important for the relay activities. They're all very important. The United Arab Emirates has the Hope orbiter, which is doing some unique measurements. And then China has an orbiter, which actually has a pretty good imager. Not quite as good as MRO, but it's pretty good. It does very high resolution images of the surface. So looking at what the Perseverance rover has done, we can kind of look at the history of what it did. It landed here in Jezero Crater and did a little side sweep over here, looking at some interesting things, took a number of samples and kind of went around this rough area here, but the Ingenuity helicopter could actually fly over the rough terrain and do some scouting ahead, so that was very useful. And then this is the Three Forks area where there's 3 different river forks that came together here. We took a number of samples there. The reason is we wanted to leave a cache of samples here. There's 10 sample tubes that we deposited here in the event that the Perseverance rover becomes disabled in the future, is not able to return samples. We do have a cache of samples that would be valuable for return. And then the Perseverance rover went up the crater wall over some of this fan of debris from river channels. Went up around this crater here, went up towards the crater rim, and Ingenuity had 72 flights that ended up kind of having a bad landing on a sand dune where one of the propellers kind of dug into a sand dune. But the actual vehicle still operates, and we can still get radio messages back and forth. It can still charge the batteries and send radio signals, but it can't fly anymore. And then we ended up here at this area where we took the Chiava Fall sample. That was in a riverbed that had some ancient mudstones there, and I'll talk a little bit more about that later. And now Perseverance continues around on the rim of the crater, gathering some really interesting samples that we hope will be able to return to Earth. So Mars sample returns, the topic of discussion. We continue to collect scientifically valuable core samples for potential return to Earth. And the Chiaba Falls sample, is particularly interesting. It may have compelling evidence of ancient microbial life on Mars. So 3.5 billion years ago, the conditions on Mars were very similar to the conditions on Earth. There was an atmosphere that could support liquid fresh water on the surface. We know that on Earth, once the conditions became habitable for life, microbial life arose very quickly. And so on Mars, we wonder, did the same thing happen on Mars? Similar conditions. So addressing the cost of Mars sample return, we have been looking at ways to implement a cheaper mission. And the key is the MAB. The MAB is very heavy. And so that drives the mass of the whole system and therefore the cost of the whole system. So we are developing a new MAB design concept that's smaller. And we're looking at a way to deliver a smaller lander using our proven side crane approach where we can just drop it down on the surface like we did Curiosity and Perseverance. And so that would also be a cost saving because now we're just rebuilding the system that we already have. And of course, industry is looking at alternatives for a large lander to bring a MAB to Mars and be able to bring the samples back. And so NASA still has not made a decision on Mars sample return. The funding for that is still in question, but we still do have people working Mars sample return at JPL and at other NASA centers. And ESA continues to develop the Earth Return Orbiter to bring the samples from Mars orbit back to Earth. They're fully funded, and they do plan on building that orbiter and launching it. So I just want to, there's a little yellow box down here, and I need to make sure I make it clear that this is a concept. Mars sample return is not a program that's been given the go-ahead, and so I'm giving this information just to let you know where we stand right now. So Mars Exploration Program has released a future plan that incorporates inputs from across the planetary science community, and we do have a big science community, international one. There's a link there where you can get this future plan. It's a fairly long document. So looking forward, we plan to implement a sustainable portfolio of missions that can address our critical and aging infrastructure. You know, the Odyssey and MRO are getting kind of old, and we could lose our high-resolution imaging capabilities, so we'd like to have a replacement for that, and also to replace our relay orbiters and many other capabilities that we have for science instruments. And we want to take advantage of the expanding commercial space business environment. I'll talk a little bit more about that later. And of course, to help prepare for human exploration of Mars. I'm a big fan of humans to Mars, and I think sending humans there would give us the best chance of finding compelling evidence for past or possibly even present life on Mars. So looking at some of the images there's on the upper right, there's the Mars Science helicopter. That's sort of where we'd like to go after the Ingenuity helicopter and be able to do some really unique science from the helicopter, getting to terrain that we can't get to anywhere else. And to access subsurface ice, we need to develop deep drilling. So we definitely are pursuing technologies to do that. So some of the future Mars planned science themes are exploring the potential for Martian life and, looking at past and present life. So the upper right sample is the Chiaba Falls sample. That's mudstone, and you can see sort of a zoom in close up of this leopard spot on there. So when we see rocks like this on Earth, usually this type of rock, which looks just like this, with those leopard spots, is evidence of past microbial life. And so that little ring of minerals there is one results of microbes having eaten and reacted with some of the minerals in the rock. So the Chiaba Falls sample, that doesn't mean that it is
evidence of past life, but it's compelling. And so there are other ways that you can get a mineral formation like this. They generally involve having high heating of the minerals to get these chemical reactions to happen. We actually don't see evidence of heating in these samples, but the only way we'll know for sure is to actually bring the sample back to Earth. So to me, that's very compelling evidence to bring back those samples. We want to support human exploration of Mars to collect science that's synergistic with objectives for human exploration. That's looking for evidence of subsurface ice that can support resource utilization. And also the weather, being able to characterize the weather for entry, descent, and landing. And then to do experiments for ISRU, in situ resource utilization. And for science part, we want to continue to reveal Mars as a dynamic planetary system. There's sort of this cutaway of what Mars might look like underneath the surface. We know that there is a lot of subsurface ice, and every now and then we see some evidence that there might be subsurface liquid water, and that's something we want to continue to explore. And what we learn about Mars helps us learn about not only the Earth, but also as we study exoplanets around other stars. Each of these planets in our solar system is a laboratory for what we might expect to see in other star systems. And so when we look at what the Mars atmosphere is like, what the Venus atmosphere is like, we hope to use spectrometer measurements from exoplanets to try to characterize planets around other star systems. And this all helps us with that. So looking at future Mars opportunities, what we want to do in our future plan is to establish a regular cadence of science-driven missions. And that runs the gamut from low-cost missions, which is what Robert was talking about, doing a lot of low-cost missions. And we are looking at options for that. Medium-class missions, and also missions of opportunity that might be competed payloads or ride shares with other missions that are going to Mars, maybe even commercial missions. And some of those could even be possibly flagship-type missions. So the low-cost missions are around the $100 to $300 million range. Medium-class missions would be a little bit more. And then there's the missions of opportunity. So you can read more about those in the future plan. So some of the things we'd like to do are monitoring and predicting Mars weather. We know that there is methane that seeps out under the surface of Mars. The Curiosity rover has a methane detector, and we occasionally see methane. It tends to be seasonal and Gale Crater. And so it's possible that the methane could be from subsurface microbes generating methane, or it could be for some kind of subsurface geothermal activity. And so we'd like to learn more about that. We'd like to be able to determine the location and nature of those methane seeps. We want to do ice mapping from orbit. There's been an international study for the International Mars Ice Mapping Mission. And right now that's not been approved, but it's still being studied. A lot of work has gone into that to try to characterize where the ice is on Mars. And then in the decadal survey from the National Academy of Sciences, they make their decadal recommendations, and one of the higher priority missions is the Mars Life Explorer, MLE. We also call that the Search for Life experiment. And so that would be to go to a region like Arcadia, we know has subsurface ice with only a very not very deep layer of topsoil on top, maybe a meter or less of topsoil in some locations. So we'd like to drill down into the ice and actually have a life detection experiment, as Robert was pulling for, to see if there might be microbial life that exists in the ice at a depth where they would be shielded from the galactic cosmic radiation that we see on the surface of Mars. And of course, supporting human exploration. So we have some images of places we'd like to go. This is an image of an ice scarp that comes from MRO. And so this is a glacier of ice that's about 100 meters deep, and it's mostly pure fresh water. And there's so this is a vertical cliff. It's hard to tell from the image. And then this is a flat surface on top. And there's only a very minimal amount of regolith on top of this ice, but that kind of protects it thermally. And so this has been here for billions of years, and it's just waiting there. There are a number of sinkholes on Mars into lava tubes, and we'd like to fly a helicopter or other type of rover into those tubes. There's an image of a concept we've developed a lot of prototypes for a two-wheel cave explorer on a tether. We also have a cliff explorer that we've developed. It's like a spider, and it has insect-type arms that can stick to the walls and climb up and down cliffs or go into caves. So these are all concepts that we've studied, and we would like to potentially do missions using those types of vehicles in the future. There are a number of companies that have expressed interest in providing commercial service carriers for delivering multiple spacecraft to Mars in different ranges of sizes, and that can include flyby, defense orbital missions, and or lander missions. So NASA did fund studies last year for a number of commercial concepts, and there is a NASA website where you can see the result of that, and that's where I took these images from. So Firefly has a concept for a commercial Mars mission. So does Impulse Space, Lockheed Martin, Robotic. Blue Origin has their Blue Ring system, which can be adapted to send multiple payloads to Mars. And then ULA has a concept using their upper stage with a sunshade. That's actually a LOX hydrogen system to carry a number of payloads to Mars. And we've been looking at a low-cost rough lander concept at JPL. And so this low-cost EDO concept would avoid the airbags, the terminal descent rockets, and expensive hardware and software. The landing shot's about 1,000 Gs, but we have instruments and we have electronics that can survive that. In fact, over here, we have a drop test tower at JPL where we can actually simulate the landing velocity, which is anywhere between 50 to 100 miles an hour when it hits the surface. And we have sort of this mechanical shock absorbing system that works pretty well. And so we did a simulated landing on Mars with this type of a system. And in here, we actually had an Android cell phone, just like my Android cell phone. And so after we did the drop test at 1,000 Gs, we took out the cell phone. It worked just fine, which is really good because we didn't have to make a claim on the insurance we had for dropping the phone, to replace the phone. That worked out fine. So you can see in this EDL diagram here, this is the way we typically do EDL at Mars. We have aerodynamic deceleration. We do a supersonic drone chute to slow us down even more, enough where we can deploy a big main chute without shedding it to pieces. That's why we have to have the drone chute before we take out the main chute. And in this concept, we just slow down the parachute all the way to the surface. And so that's where we get like a 50 mile an hour to 100 mile an hour impact. And we're pretty confident after our testing that we can build systems that can survive that and maybe even have small rovers and do different kinds of science experiments on Mars and deliver these payloads in a much cheaper manner than we have in the past. So let's see, I'm going to show a video here. I can get that going. So this is, the Mars Science Helicopter chopper concept. So this is a 6-blade system, going through canyon like Mariner Valley, Valles Marineris, being able to look at the layers on the side, being able to go into rough terrain and fly around. We've done some development tests with this type of system. I think there's another scene here. Yeah, and so this is another scene of a chopper just flying over rough terrain, getting these areas that we couldn't get to with typical type of rovers and examine some interesting things. So, and let's see. Oops. Okay. And then there's another concept that we've worked with AeroVironment. AeroVironment was a partner for the Ingenuity helicopter. And so AeroVironment did this video here of something called Stifle. And so this has some similarities actually to Dragonfly on Titan in that we come in on a parachute and then we drop the heat shield and we actually deploy the helicopters mid-air rather than landing them. And this is what Dragonfly plans on doing on Titan. But these are sort of advanced versions of the Ingenuity helicopter that can fly off and go in different directions. And of course, this saves a lot of money because we don't actually have to have a lander that lands on the surface. We just deploy things mid-air. And so these helicopters could go out in different directions and do parallel scouting of areas on Mars. And we're looking at ground-penetrating radar that these things can carry to search for water, subsurface water, and also scout out humanoids. And just to give you a perspective on how the helicopters are working, they would be solar powered. And so they would have to charge up with the sun for a whole day. And then after they charge up, it can generally operate for something like about 3 minutes, which is similar to what the Ingenuity helicopter did. But But Ingenuity could fly pretty fast, and these helicopters here could also fly fast. So, in 3 minutes, you can actually cover quite a bit of ground. So, some closing comments. NASA currently has a thriving Mars exploration program with orbiters and rovers that continue to provide groundbreaking science discoveries. The Mars exploration program is exploring a wide range of concepts for exciting and scientifically valuable future missions that can fit within the expected funding environment, which is a little uncertain right now, but we're all doing the best we can. And then commercial services and partnerships would be key to successful implementation and bringing down costs. And we do have funding for new technology developments. And so we are actually developing new technologies for power sources using radioisotopes other than plutonium, like americium-241. So they would be potentially cheaper and more easily available to power some of these systems. Advanced electronics and entry, descent, and landing techniques like the rough lander that we saw there, and then advanced concepts for science instruments to bring down the mass and the cost, and also to be able to do new kinds of measurements that we haven't been able to do before. And of course, paving the way for human exploration of Mars is a driving goal. And with that, I'm happy to take any questions that people have. Yeah, back there.
I'm interested in exploring a bit further the search for life and what you mentioned about methane.
Yeah.
I understand one can't distinguish between biogenic and abiogenic methane based on the C12, C13 current isotopes. Not easy to do. And I'm wondering if there's any plan to deploy instrument packages to Mars that it would be able to distinguish whether the methane is likely biological or geological origin. In the larger sense, for the search for life, when I went to Coast Guard in 2018, I attended the planetary protection panel presentations there. They were very clear at that point. They took a dim view of landing in the places where there's most likely to be life on Mars. They wanted to keep missions away from there in sample returns. Has anything changed in the last 7 years? Can we go where life is most likely?
Right.
Missions at this point, or are there still planetary protection obstacles?
So we're still adhering to those Coast Guard recommendations, and we have a planetary protection officer at NASA. And so we put a lot of effort in our MLE experiment that was in a decadal survey to show that we can have a sterilized system that can drill into the ice and be able to take measurements with systems that are all sterilized so that we can be assured that we're not injecting any Earth microbes into that. And I think a good test case is actually the sample tubes that we had on the Perseverance rover. So we had a requirement on Perseverance that the sample caching area and the tubes had to have less than 1 microbe on them. And so we went through this tremendous verification program, and I think we demonstrated that the system we have on Mars right now with Perseverance, the areas that are contacting our samples don't have any microbes on them. So that way, when we bring back the samples, if we see something, we can hopefully be assured that it's not an Earth microorganism because we didn't send any there. But just to be sure, we also take these swab samples of everything in the clean rooms, and we do a genotyping of them, and we have them all in a database. So if we see something coming back from Mars, we would definitely check with our genomic inventory database to make sure it wasn't one of the critters in our clean room. And we do have all kinds of critters on the clean room that have evolved to survive only in clean rooms. Life is tenacious. But anyway, we have pretty good confidence we'll be able to meet the planetary protection requirements in a search for life experiment.
And characterizing methane, are there any instrument packages that might be deployed to Mars that are under development?
People are thinking about that. So I think the first thing is to actually find out where is the methane coming from, and that might give us some clues. But then also, as you mentioned, isotopic measurements of that would also be valuable. And also for future sample return missions, it's possible we could take samples of the methane and bring it back. For Mars sample return, we do have air samples, atmospheric samples, just for similar type purposes to look at the atmosphere on Mars that we would bring back and be able to examine a pristine sample of the atmosphere. Okay, back there.
So, you mentioned that rough landing concept that you guys were working on that was able to protect an Android phone from, what was it, 1,000 Gs?
Yeah, 1,000 Gs.
Would this be something that would maybe theoretically be implemented in human missions, or would that be considered too risky?
Oh, to send humans on a rough landing like that? Well, it's interesting. There was this movie that came out that had humans going to Mars, and they had a problem, and so they had airbags, and so they had surrounding the airbags. So, yeah, I think that would probably be a little cruel to send people with a system like that, and you certainly wouldn't do the rough landing. But yeah, no, I think for landing humans on Mars, we want a nice soft landing system. Yeah.
Thank you. And just thank you again just for presenting to us and for everything that you and the teams do. Very much appreciated. Question on the data relays. I've read that DTN, disruption and delay tolerant networking, could be part of future relay architectures. Just wondering if that's part of it, and if not, what would be the threshold in terms of mission distance or complexity where that technology may be introduced?
So you've now reached outside my area of expertise. But I can tell you about our current relay system is we have a UHF communications between our surface assets and our orbiters. And so that's how we get the data back and forth from our surface assets. And so in the near future, we plan to continue to use those UHF links because we have all kinds of systems that have been developed, and they're in a number of different international orbiters. And so we're going to probably stick with that for a while. And then to get the data back from the orbiter to Earth, we use X-band, we've used K-band, and in the future, we'll probably use optical communication. And then also, we know that SpaceX has been looking at a version of Starlink at Mars. And so again, you know, if we speculate off of what they've done with Starlink, they would probably have laser cross communication amongst their Mars orbiters. And then as far as the link to the surface assets, I think that's a decision that would be made for the future. But as we look at for humans to Mars, definitely we need to have a very robust data relay system around Mars that can have continuous communication with the surface assets, the people, and also being able to send lots of data back and forth.
And could you talk a bit about some of the fundamental reasons why Mars sample return has to be such an expensive mission?
I think a lot of it has to do with the Mars ascent vehicle and how large it was. And so for us, the big challenge, that's a big lever because, you know, you have this gear ratio. Anytime you're landing something on the moon or Mars and you're bringing something back, you know, it's the thing you're bringing back is the big lever, and how massive things are and how much they cost. And so really the key to bringing down the cost is reducing the mass of the map and the volume of the map too, because you have to fit in the volume. So that's really what we focused on, and we think that we've made progress and concepts that can do that. And one of the keys is actually using lower mass avionics. So the concept we're looking at now for the MAV uses more modern electronics, like what's in a cell phone, like what was in the Ingenuity helicopter, rather than the more massive avionics we've had on our orbiters.
Next is a clip of David Malott, CEO and founder of SpaceFactory.AI. He presented about 3D printing habitats using Mars regolith called MarsHa.
So our Mars habitat, or we call MarsHa, has a number of unique aspects to it. So one is just the sort of unique design that's been called sometimes an egg or a beehive. It's very much a result of trying to create an efficient pressure vessel. So one of the big drivers of the design is that the Mars atmosphere is very thin compared to Earth's atmosphere. So the interior of the habitat would want to push outwards on the structure. And then hence this very efficient egg-like form to contain that internal pressure. The other thing was this extreme temperature fluctuation. And all materials and structures will expand and contract with temperature. So the solution here was to disengage the interior floors from that external shell so that we could actually allow the external shell to expand and contract while the internal shell supporting the floors could remain static. And by doing this, we greatly relieve the amount of mass that would have to go into building this structure, as well as setting up conditions like the stairway that would occupy that space between the inner and outer shells. So a little bit of architectural innovation happening there.
Coming up next is Erika DeBenedictis speaking about a path to a green Mars.
And when I think about space travel, I think it's a huge challenge and also invitation for us to reimagine how we want civilization to work. And I love the idea of challenging us to actually achieve something mutually beneficial when we go to Mars. Girls just want gardens on Mars. I want like less chrome geodesic domes and more us going to this place and learning how to make it thrive and not just for the humans. So for the rest of the talk, I want to circle back around to talk more about Pioneer Labs and what we're working on now. So our goal is to create the organisms, the pioneer species that would be necessary to make Mars a nicer place for more life to live. That starts again with the very first microbe that you might actually deliberately use on Mars to do something useful. And to be really concrete, we spend most of our time thinking about what could you possibly flight test in like the 2031 launch window that would be independently useful and also de-risk every, a ton of the basic science questions that we have about things that happen to the right. And we spend the minority of our time thinking about how does that first flight test facilitate or tie in to some of these larger, terraforming endpoint visions. Now, if you're going to do a flight test, and it's going to be very expensive, you have to have a really good reason to do it. So we have tried to spec out what a possible mission in 2031 would look like. And I'll describe it with sort of two sets of requirements. So on the left, no matter what you're growing, what we know about today is carbon-based, water-based life. And so there are some non-negotiable universal atomic requirements for the materials that you need to have on hand to grow that life. Your life needs to get carbon, nitrogen, phosphorus, sulfur, and then like a long tail of like little extra heavy metals and stuff like that in order to grow. And ideally, in order to work on Mars, you want those raw materials to be sourced locally. You want to do ISRU rather than bringing everything with you, because then what's the point? On the right, there has to be a reason for this to happen. So an ideal 2031 flight test would be useful. It would have some sort of useful outcome for either robotic or human missions. It would de-risk the fundamental science. Do we really know what's in the soil? Like, is there an impact of growing slightly lower gravity, stuff like that? And then also very crucially, this is now not actually that far away. There's going to be ongoing search for life missions. And it's important that at this stage, any organisms we deliberately send to Mars really actually cannot terraform the planet. They can't grow outside. They really are, fully domesticated and need us and our artificial environments to grow.
Stay tuned for Vicky Hamilton from MEPAG, the Mars Exploration Program Advisory Group.
So here's a fleet chart of NASA missions and some of our international colleagues' missions to Mars in the last 20 some odd years. And what you'll see is that there's a whole suite of landed missions, rover missions, orbital missions that all complement each other. And Mars exploration as a program has been so successful because it takes what we learn from early missions and takes that and adapts it and builds upon it and complements it with the subsequent missions. And so you can see kind of what we've been doing in the last 20 some odd years and where we hope to be going in the immediate future. But I think what I'm talking about here is really well graphically represented in part by the arrows at the bottom of the figure. So back in the very late 90s, early 2000s, we learned that there was in fact water on Mars, in Mars, beyond its presence at the polar caps. And so that led us to many missions and instruments and investigations focusing on where that water is. And that, of course, leads us into the idea of habitability and where are habitable locations on the planet Mars. And then that, of course, brings you to the question of, well, who was maybe habiting it? Is there evidence of fossil life on Mars? And now coming into the next several years and decades, probably, of exploration, we'll be looking for actual signs of extant life, not just fossil life. And of course, interwoven throughout all of that is how Mars exploration feeds forward into the preparation for human exploration.
And lastly, listen to Abigail Freeman, Deputy Project Scientist for Curiosity, speaking about her 13 years of research on the Mars rover.
I have to start off with what we saw yesterday morning when we came into work and we all had to plan what to do over the weekend. This is where Curiosity is currently parked. We're looking at some really interesting rocks that you're calling the boxwork structures. And let's see if I can pull up a laser pointer. The boxwork structures, we call them that because they look like kind of boxes. And it's a series of ridges and hollows that we're investigating, trying to understand what were the processes that formed these different ridges and hollows. We think groundwater was probably involved, and we're wondering, was it a process where water came up and it formed some sort of cement? What was the kind of water that was involved? Was it really salty? What was the temperature? Was it something that was lived? Did it happen very quickly? How did that affect the rocks? And so we're having just a wonderful time exploring these sweet enigmatic features. At the moment, we're looking for a place to hopefully drill some rock samples to put into the Ward laboratories on Curiosity. And so we have a little bit of fun into one of these hollows that we'll be doing over the weekend. Coming on Monday, hopefully there'll be a piece of rock. There's very many rocks in the hollows, but there's one little one right there. So hoping something like that will be in front of the rover, and we're going to set us up and hopefully drill next week or the week after, figure out what they're needing. So I'll just end with a teaser for the road ahead. We're going to continue climbing Mount Sharp. This is a view into the top of the mountain. This is what we call the Yarday unit. These are really enigmatic. We don't know what these rocks are made of. We don't know how they formed. They might be reflective of a whole regional unit that's called the Medusa Fossae Formation that we see other places on Mars and is also super enigmatic. So I'm super excited to keep roaming and get there hopefully one day and figure out what this tells us about an even earlier part in Martian history. And I'll end with our beautiful postcard that we took just a couple weeks ago with our tracks in the distance as we made our way across the boxworks. So thank you very much.
If you enjoyed these clips, there are more talks from the convention, which can be found on the Mars Society's YouTube channel, including with Dex Hunter-Torek, who will be featured on a special edition episode broadcasting Saturday, November 15th at 11 a.m. Pacific time. We hope to see you there. And as always, the best is yet to come. See you next month. Bye.